Hello, everybody. Welcome to Autodesk Fusion Generative for Manufacturing. My name is Mike Fiedler, and with me also is Apollo Vanderberg. We are enterprise simulation specialists here at Autodesk, and we are going to walk you through today's topic. We also have Anton Fedosayev, one of our colleagues here at Autodesk, and he will be helping also with some information and some of the questions. So let's go ahead and get started with the information that we're going to share today. Let's start out with the agenda. Of course, we have the welcome, and then we're going to talk about what is generative design in terms of manufacturing. We will also provide a brief demo for you with the software, and at that point, or at the end of that brief demo, Apollo will also have an example up within the software. So after we go through the demo and we talk about what the next steps are if you want to learn more in regards to the product, then we will have available time for a question and answer session. So if there's anything that you see during the demo or anything that you don't see during the demo that you would like to know more about, we can certainly jump into the software and show you how something like that might be accomplished, or where you would input something like your question into the program. So certainly we encourage a lively discussion when we get to the question and answer portion of the presentation. So let's go ahead and start with perhaps the first question that you might want to ask, and that's, why do we care? Right before anybody tries to give me some sort of software, you know, we are part of Autodesk. Autodesk has a lot of different software programs available to the users, and not only just within the Autodesk family, but whenever somebody tries to introduce or introduces a new program to me and says, hey, look at this really interesting product, my first question might be, do I need to learn a new software? Why do I care about it? How is it going to help me? So we wanted to address that question right from the very beginning. And so we got a couple of examples here. On the left-hand side, you can see a General Motors seatbelt bracket. And what they did was take a multi-part assembly and utilize generative design to do some part consolidation to make that into a single component that was generatively designed. And really there's two reasons, at least, why you might want to do that, and you can see those on the slide there. One would be optimizing it for mass, right? So being able to take that assembly and lightweight it, maybe particularly with an eye on the future. I guess I could say the future is now, right? With electric vehicles coming, right? Mass is very important. The range of the electric vehicle is certainly very much influenced by how much weight the vehicle needs to move, and in addition to the aerodynamics of the vehicle and so forth, the capacity of the battery, things like that. But weight is a very important factor there. And then also, you know, when we take an assembly and we consolidate it into a single component, then of course we get to reduce the supply chain costs associated with, you know, having each one of those parts and also tracking where they are, having a place to keep all those different components, and so on. So I think I talked enough about that one. Let's take a look at the one on the right-hand side there. This is a company called Disrupt Disability, and they are working on making wheelchairs more versatile, making them customizable, and also making them, to a degree, a fashion item, if you will, right? Kind of unique, as opposed to what we have seen the same design for so many years. So a couple of the benefits there, we are able to tailor it to each person's measurements. So we could start out, perhaps this person first approaches the company when they are a younger person, and then as they grow up into adulthood, then of course, you know, the components could be swapped out and tailored towards that person's measurements, and also interchangeable based on their needs. So we could have something maybe very lightweight that is used or tailored something more towards around the home or office or street use, but if this person decides that they want to get into something, maybe an environment which requires something that is maybe more suited towards like an off-road type of application, then we could change out those parts for something that's maybe a little bit more durable. So what I'm trying to say with these two different examples here is the software is in use. People are exploring different applications with it. So it's not some sort of future software. It is something you could certainly take advantage of now and see if it is something that would be useful in your environment. Okay. So we talked a little bit about maybe some of the whys you might be interested, but what is it exactly? And I think the first sentence here kind of summarizes it nicely. Certainly the whole presentation here is geared towards what is Autodesk Generative Design, but in a overarching statement, what I would say is it's a design exploration technology. So the images on the right-hand side there, the light blue chairs, it kind of alludes towards the benefit of the software, right? It generates a lot of different CAD-ready solutions based on real-world manufacturing constraints. And that's really where the time savings are for you. And let's dig into that idea a little bit. So imagine that your boss comes to you and says, hey, we're going to create a new product. And either you or a small team is dedicated towards coming up with this product, right? What's one of the first things that you do, or even just a redesign of the product? You come up with a few different concepts, right? You might have so much time allocated to that. Maybe you have a meeting these days, I guess, a virtual meeting, some WebEx or Microsoft team meetings to talk about some different concepts that you have come up with, right? So a person's able to think of a few different concepts. And then of course we know that those concepts ultimately need to be validated and produced. So before we get to the validated concept that we are going to produce, of course, we need to evaluate those. And some people might come into this meeting and they might say, well, we can't utilize this material because it's too expensive, or you might have somebody there from production, perhaps one of your machine operators, and they might come back and say, this isn't really manufacturable the way that this would be designed. It's pre-designed, but we can't manufacture it. So you kind of go back and forth, right? And you test out these different concepts until you come up with one that can be validated and ultimately produced. So if we look at the cycle here, we might have a fairly lengthy iteration phase, and then also a reasonable amount of time that goes in the design to production until you end up with something like this motorcycle swing arm, or we're going to dive into an example here of a motorcycle triple clamp, right? So maybe in the top part here, starting with our existing design, what we want to change, and then what we end up with in the end of a traditional redesign process. So let's contrast that with the generative design and why we say it has improved productivity. Well, with generative design, the outcome of using the program is multiple validated manufacturable options. And the reason that we are making that statement is because what goes into generative design. So Paulo a little bit later on is going to go through the walkthrough of the software, and what you'll see there are the inputs to it. So just at a high level, what are you putting in? You're defining where my constraints are. That is, where is this thing held? Where does it connect to something else? You are inputting into it what sort of loads it needs to withstand, some forces, maybe some moments. You are defining different types of materials that it might be made out of. So you can give it 4 different, 5 different, 6 different materials. And then you are also giving input to the program ideas as to how you might want to manufacture it, whether it's a 2.5 axis mill, whether it's going to be 3D printed. And then given all that input, generative design is going to come up with multiple outputs. And so you can take a look at one of those and say, okay, Here's what our output is. Maybe if we just explore this one as a die cast part, and it can also give you some idea as to what the cost might be and what the mass might be. So you can see with this outcome, the cost is relatively low, but the mass still kind of high and maybe not as low as we might like it to be. So we can explore one of the other outcomes that it gives us. And again, once generative design has done all of its thing, the act of exploring these different outcomes is very easy and quick to do, and we'll show you a little bit more about that as we go through the demo and some of these slides. So as we take a look at one of its other outcomes, maybe this one is an additive outcome. So potentially here our cost is pretty darn high, but we know that we can get a low mass part out of it, which is perhaps something that is attractive. And if we take a look at a different outcome, this one using a 3-axis mill, the cost is of course lower than the additive outcome perhaps, but then the mass is a little bit higher. So a little bit more traditional manufacturing method, and the mass perhaps while higher is tolerable. So after you explore all these different outcomes that the program has produced for you, ultimately you can decide on one. You can see an example here with a 2.5-axis CNC aluminum part. It's the right balance for what you are trying to produce in terms of cost and mass. So we're really trying to help in the time to market by really shortening up the time to produce all these various outcomes, and then it's really up to you as the user to determine from those outcomes which one strikes the right balance for what you need to do. Okay, the next thing here that we're going to do is contrast generative design with topology optimization. So topology optimization exists within the Inventor program, within the Fusion program, and you'll probably also see it from some different vendors. But what we want to do is differentiate or make clear what the differences are between topology optimization and generative design. So what is topology optimization? Let's first explore it in terms of a transportation analogy, and we'll talk about a shipping route. Right, so you need to take products from point A to B, and that's really equivalent to your existing product. So we have a product, and we know what it costs to manufacture it. We know how much it weighs. We know how strong it is, etc. And you decide that you want to make a lighter weight part. Well, that's basically what topology optimization does. It's equivalent to finding a faster shipping route for you. It removes material in topology optimization. So you know that you can get a lighter weight part, right? So that's what topology optimization does. And it would be the same as going, well, instead of going from A to B, we can go through the Panama Canal, and it gets us 60% faster, or in terms of your part, 60% lighter perhaps. When you utilize generative design, it will do that too. You can take an existing part and figure out how to make it lighter, but at the same time, in terms of the transportation analogy, it also will find a trucking route, it'll find a train route, it'll find a plane route, right? And then map all these out. And when we take a look at these, they all are capable of carrying different amounts of cargo. They go at different rates of speed. They have different security and cost associated with them. So this is the same as when you utilize generative design, you're going to get those different manufacturing methods. You're going to explore different materials, right? So we're going to lay all these out. They have different costs associated with them, and then you can determine, what is the best for you. So nothing against topology optimization. It's just that generative design is going to give you more, right? There's more that goes into it, and there's going to be more in terms of the outcome. So nice in regards to that. So when might you utilize generative design, right? You say, okay, I'm a little bit sold on the idea of generative design. At what point do I bring it into my process? Is this just to give me new ideas? Is it for existing parts? When do we use it, Mike? Well, we think that you can use it in multiple cases. One would be with new product design, right? So if you don't know necessarily how you're going to approach this new design right from the get-go, generative design is great for that because you can explore different materials. You haven't maybe yet defined a material for this new part exactly. You might have some ideas, of course, based on the strength and cost, but generative design can help you decide that. It can also help you decide the manufacturing methods, which maybe haven't been determined for this new part yet. So it's absolutely fabulous for new part design. It can also be utilized for part consolidation, like we saw with the GM seatbelt bracket, right? So you might just want to take some existing assembly, which might be costly or hard to manufacture currently, and figure out, how can we make this out of a single component and all the cost savings that come along with reducing an assembly or the amount of parts that are in an assembly. And then lastly, we already talked about it, part enhancement. So if you do have existing parts, by all means, you can take that existing part, run it through generative design, and look at some alternatives as far as what that design might look like. How can I utilize different materials, or how might I utilize some different manufacturing methods? So all three of these we think are good uses of generative design. So the next thing we're going to talk about is striking the right balance between performance and cost to produce. So I think the bottom sentence here is a really powerful statement. So engineers are limited in the time and energy that they can spend on any design problem to fully explore the options that encompass the design space. We are in a slightly different line of work here in what our roles are at Autodesk. But I understand that engineers are limited in time, right? We are always trying to move ahead faster and find ways to save money. And really, generative design is able to help with that, right? By producing many different outcomes for you. So you don't have to ideate yourself or with a small team all these different ideas. The generative design really helps out there. And then it's up to you. The part that you're going to focus your time on is what's right for me as far as the performance of the part from all these outcomes, and where do I want to be on cost of this part. So really balancing these two things, cost to produce and performance. So let's lay it out again in terms of a transportation analogy. So look at something that everybody can be familiar with, right? Instead of a part that might be unique to something that I've seen or a part that you've seen. We're all familiar with cars, right? And we know that if we look at the performance and cost to produce, you can spend very little on a car, or at the other end of the spectrum, you can spend a whole lot of money on a car, and there's a lot of choices in between there. And certain manufacturers kind of focus on the one end of the spectrum, and other manufacturers are elsewhere along this price performance curve. So when you are coming to market with your product, you can decide where you want to be. Certainly this is quite complex, perhaps with a vehicle making those decisions and all the components that go into that vehicle. So hopefully maybe your challenge is not quite that difficult. Let's take a look at something maybe a little bit simpler. So this is a bracket from GE Aerospace, and GE Aerospace had decided, well, we want to come up with some different designs on this. Perhaps it's costly to produce as it was. Maybe not so much, but perhaps maybe they didn't like the weight of this part. So what they did was they put this out there to the user community on GrabCAD as a challenge, and they said, hey, look, here's our geometry as it exists today. And they informed everybody, this is where the part is constrained within the 4 bolt holes that you see on this. And then we're going to apply some loads, and they identified what those loads were in different load cases. So there was a vertical load, there was a horizontal load, there was an off-axis load, a moment, and they asked the user community, hey, can you guys come up with some, and girls, can you come up with some different designs for us? And the user community delivered. Lots and lots of users delivered lots of different designs, and you can see some of those different designs here. So that's completely awesome. I loved watching this unfold and seeing all the different designs. But what's the downside of this? You know, can you always do that? Can you always community source your design, right? So I think the reasonable answer to that is no. Generally, you're going to keep this in-house, right? So how many times or how many different designs can your people come up with? How much time can you give them to come up with all these different designs, right? And how many different designs can be thought of? You know, if you give it the assignment to one person, you know, you have time to come up with a few ideas, and then you make the team a little bit larger. Maybe you get something a little bit different, right? Um, but anyway, this is really what generative design is designed design optimization is really here to help you with, is to come up with these different designs, and then, you know, once you have all these different outcomes, you can decide where you need to be along the price to performance curve. All right. And speaking of pricing, so generative design also has partnered with a priori, and one of the outputs, you know, we talked about it's going to give you a lot of different outputs, and this is one of the output screens that you get. And you can see that there are quite a few different outcomes here in the different colors. And the different colors associate with different manufacturing methods. So and then on the left hand of the spectrum there, you can see the estimated manufacturing cost. So that is why you kind of see some what do you want to call it? Some ranges here. So you know, we can't say that it's going to cost exactly $600 per component to produce, but it'll give you a range, so you have some idea about, you know, where that might exist in the cost to produce. And so that's one of the ways that you can evaluate that. You know, maybe you say, well, I want to use these manufacturing methods. These ones here on the horizontal spectrum would be the mass. So, you know, maybe you don't want to go over here towards things that are maybe a little bit too heavy, and maybe these ones are a little bit too light for what you need. So you're going to focus on these ones here, and then you can kind of start to whittle down the outcomes to those ones of focus based on, you know, where you want to be in terms of cost. And certainly as Apollo goes through his demo, he'll show some of the other screens that you can utilize to evaluate these different outcomes as well. All right. So with that, I'm going to go ahead and let Apollo begin to show you a little bit more about the program.
Yeah, thanks, Mike. And so there were a couple questions too, asking around, you know, how to set certain things up, and you know, maybe some of that will be covered by this quick demo here. And if not, then when I start sharing my screen, you know, with Fusion open, we can, you know, get into more specifics. But you know, as a whole, you know, the big thing is, as Mike mentioned, you know, we have a couple different mentalities, whether we're doing this for new product development or part consolidation or part improvement. And so ultimately there is, you know, maybe from a part enhancement in this example, you know, we have existing CAD. And so we have to, you know, start from that CAD and project certain geometries that will help us define, you know, where our loads and constraints are going to be, how we want to represent that this part, you know, what it experiences in real life. Then we generate all the different solutions based off of the materials and manufacturing methods we're looking into, and then, you know, spend time exploring to understand, you know, how those different parts are responding to those load cases, and you know, which one we might want to move forward with. So if Mike, you go to the next slide. You know, when we talk about the manufacturing methods, you know, Mike mentioned a little bit of this. We are manufacturing aware, so we're not just producing, you know, an unrestricted, you know, what's the lightest weight or you know, most intricate part we can design that meets those loads. You can definitely get that, but if you want to constrain it to additive in the sense of you have a specific printer and certain overhang angles that you can, you know, can or cannot tolerate, you know, with die casting and looking at draft angles, you know, based on your milling machines, you know, what size bits do you have, and what's the tool reach, so that we can make sure we're able to cut out, you know, appropriately sized holes. 2.5 axis and 2 axis cutting, if you happen to be looking at things that, you know, may be more plate steel or sheet metal-esque. So all of the stuff we can introduce and set those constraints and have the outputs come back relative to these manufacturing methods. So, looking at this suspension A-arm, this is kind of what we're going to look at a little bit. We are first going to take that A-arm from the design space into generative design workspace. And so here we can make edits that are unique to the geometry and don't propagate or influence the primary design, which is good if we are collaborating with others, and start making those modifications. So for example, we know we have areas that are going to experience those loads where we have bolted or mounted connections to adjacent parts within our sub-assemblies. And so we're going to project some geometry there. And then we know that the suspension has to move. And so we may need things to represent the frame so that we don't get into clashing, or the fact that we have bolts and mounting hardware. And so once we make all these geometry edits, we can actually start assigning those parameters. So in the design space itself, preserves are things that we want to keep that will be included into the geometry itself, where we assign those loads and constraints. Obstacle regions are regions that we don't want geometry to be built. So those would be for tool access, for mounting hardware, or just range of motion. And then from there, we can start setting up our loads and constraints. So picking faces that may be fixed or have some pressure or some force acting on them in different angles. We can have a number of different load cases. So here I actually did a couple based on your suspension movement, acceleration, and braking. We can specify what our objectives are. So do we want to minimize mass, maximize stiffness, and set a safety factor? And then here specifying the manufacturing methods. So, kind of going through to say, look, here we have a 3-axis machine and this is the setup, it's only in one direction, or we have a 5-axis machine and we want to, set a certain drill bit size or, milling end mill size. From a material perspective, we have a wide library. We mentioned a priori and the costing. For manufacturing methods that a priori supports for a given material, you'll actually see a little calculator symbol next to it, letting you know that we will do the costing. Once you have everything set up, we can do the pre-check and then generate our solution. Once you have it generated, we can start filtering on the left based on those manufacturing methods to kind of see how things vary between them, or based on objective ranges. So maybe we know we have a minimum mass target that we want to hit, or a maximum mass target that we want to stay below, and or specific displacement. We can look at things from a tabular form and sort, by any of the columns as you see fit. And then like the big ones tend to be, as Mike was showing, the graph aspect, because you can really look at all of the data at once. Here plotting the displacement versus mass. And if we want to, we see a collection that we might want to zoom into and kind of compare a little bit more. So from here, we can select those two. We can see the blue one's aluminum, the orange one's magnesium, and maybe we want to look at them side by side to see how they're different. As we toggle them, the details are on the right as far as their manufacturing method, the actual max displacement that they experienced, where the stress concentrations are within each of those parts. And then as we find that we have one that we like, we can actually take that part and promote it back into a design within Fusion, so that we can then use that for further post-processing, whether that's validation and Fusion simulation, or maybe we want to take it to the CAM workspace to see what what the milling process might be, if it happens to be a milling outcome that you're looking at. And so here we have it back into the full assembly. So if you go to the next slide, Mike, the big thing here that we want to highlight, right? It's not uncommon that as we talk about generative design, that people might have I don't want to say blinders, but a certain view on how things are presented, that it can only be an additive solution, that some of the parts aren't going to be, manufacturable from a subtractive standpoint, and that's not always the case. And likewise, a lot of the stuff that we can get into might even span into industrial design. So kind of just giving you here a little snapshot of different types of geometry that people got into and have used it for. So whether it's, headphones or, a quadcopter chassis there next to it in black, or like in the bottom right, looking at a lampshade. But then, from a automotive perspective, we had a motorcycle swing arm and brake calipers. So there's a number of different industries we can definitely get into. It's just a matter of how you break your geometry down and the assumptions that you assign into it to make sure that we are representing what you want at the end of the day. Go to the next slide. So, after this slide and the next one, I'll start sharing my screen so, we can take questions and look at Fusion, a little bit more in depth. But, ultimately, after all of this, if you say, what, I'm interested, how do I learn more? Well, really, there's two ways. So one, at the end of the webinar, as you close out, you will get a quick 3-question survey. First one being, if you'd like us to reach out to you to talk more about generative design. And so if you are, feel free to answer yes, and we'll take those those contacts and reach out to you and see what issues you have, what you'd like to get into, and how we can help. The second path is actually leveraging our customer success hub. So you can see the URL at the bottom, customersuccess.autodesk.com. Under the mechanical engineer section, and I'll have this website up too when I take over to show it, we have a generative design and manufacturing course that was posted about a month ago. So it was right around our last webinar that we did. And what we wanted to do starting here moving forward is for anybody that is maybe starting and learning the tool, if you happen to go through that generative course, which all in all maybe takes about 2 to 3 hours of your time that you can spread out as you see fit through the different modules. Our next our next webinar, the one that will be for September, will be dedicated as an office hours for anyone that has questions based on the content that they've gone through. So as you go through it, if you run into questions and you want to chat a little bit more, we'll spend a few minutes talking about maybe a couple small tips within generative design, and then dedicate the bulk majority of our next session to being an office hours for anyone that has questions on actual projects. So with that, we can open it up to some questions, and I'll start sharing on my side with Fusion. So if you yeah, have any questions, feel free to ask them, and we'll start going through them.
I'm going to start at the bottom here and the questions. There's a question here: is generative similar to a tool that makes predictions for you? How do you provide reference idea for the software to extrapolate the various designs? Yeah, take that, or
yeah, I can take that. So it's a good question. So kind of the way, kind of like you see in the demo and kind of like what I have here, the original geometry for our A arm was this, right? And so while it's you could say it's similar to AI or machine learning, not so much so in the fact that you're not, say, teaching a neural network and then trying to have it do predictions. We do have some groundings that we are starting with. So we have, the original geometry, which we can or may choose not to use, but ultimately it's a function of your preserves and your obstacles. So you're kind of defining the problem setup in this capacity. So you can see from that initial starting shape or initial geometry, I took these 4 components and said, this is what I care about. because this is where our loads, this is where our constraints are going to be. And I have a number of different load cases for acceleration, for braking, for turning. Maybe the tire is hanging down as the car is up on a jack or jack stands. So all those different load cases that would be experienced by this new component that's going to exist between these preserves, are kind of assigned. But I also have regions that I can't define, right? I know I need to have some gaps between, those two mounting brackets because that's where the chassis lies, or this is where, some of the mounting hardware for, the for steering or for the upright is going to be mounted. And so once you did define all that, that's kind of the problem setup that we get into for how the software now is saying, okay, this is where I can build geometry. Let me go build it and meet your requirements for given objectives, materials, and manufacturing methods.
All right. There's a popular question. Can generative design be applied to sheet metal?
Yeah, I'll answer that one live as well. So sheet metal is an interesting topic. I say yes and no. So it kind of depends on what you're looking for from sheet metal. This is an active area of investigation from our product team. So for some people, if sheet metal might be, I want to optimize maybe the location of lightning holes, for lightweighting and punch outs. Some of that absolutely, is available within what we have today. Other aspects that people want to get into is, maybe I want to force a given sheet metal thickness, but I want it to decide where or if I need, ribs for reinforcement, or stiffeners, other sheet metal features or a bend. And some of that, it's areas that we are looking into, but we're not going to dictate, where a bend would exist for a sheet metal component. So there are still methods you can use. So we have a really good story from another account with Claudius Peters that's on our website, where they actually deal with things in plate steel, and we're able to leverage generative design for design insight, and then use that to then build their parts out of plate steel. So might be something worth taking a peek at.
All right. I'm happy to hit the next one down on the list, and you can fill in if there's
Sure.
anything you want to add to it. Nicholas asks, excuse me, that was Bill. He said, what is the platform for the stress analysis? If you've been following along with Autodesk products for the last couple of years, a few years back, Autodesk acquired the company NEI Nastran. So Nastran is the engine for the stress analysis portion of this. And we should also mention that when you get the outcome from the generative design, you can take it from within Fusion as Apollo demonstrated in the product demo itself, exporting it back to the design environment. In the design environment, you could certainly make changes to the geometry, but you could also enter in right into Fusion simulation environment. And in the simulation environment, it's going to remember the constraints and the loads and the material that you've applied here in generative design. And basically, it's already set up as a stress analysis. So you could go ahead and hit the run button and have it execute the stress analysis, and then do more thorough study on the outcomes of that. If you want, you could take a look at the different components of the stress. You could take a look at the displacement output. You could also switch it into other analysis types as well. So Fusion simulation has abilities to do thermal analysis. You could do modal analysis. You could do nonlinear analysis, and then also very, very capable, or likewise, I guess, you could also export that outcome to, there's a partnership with ANSYS as well. So if you happen to utilize that for your FEA analysis, you can send it over there to do more post-processing on as well. But to answer the initial question, the Astran is what is being used as the engine.
Okay. Yeah, I don't have anything else to add there, but I can comment on kind of these next two. Can we say topology optimization, maybe a subset of generative design? You know, perhaps yes, you could think of it that way, that, while topology optimization is trying to get you a single solution for a setup, generative design is almost doing a design of experiment across topology optimizations for you, right? Because we are able to assign multiple constraints, whether it's the manufacturing constraints or material constraints, as well as then those load cases that would probably be, the load cases would be similar to what you might do in a topology optimization. So yeah, I would say you could potentially think of it that way. And then there's another one here asking how far ahead is generative design in Fusion as compared to generative design in Revit. I think that's a little maybe apples and oranges of a comparison. While both are labeled generative design and both are taking multiple facets to produce an outcome, to give you insights and kind of give you a path forward, the approaches are a little bit different, since the generative design in Revit is focused more on things that are pertinent from a Revit perspective. So whether we're looking at room layouts and looking at different constraints for that office layout, as to where we place desks, where we place other features, and then generative design here in Fusion, focusing more on specific parts. So I wouldn't necessarily say one is ahead of the other. It's just that they are targeted for different areas and different segments. Well, hopefully that answers your question there. There's one question on where do we find those examples. I'm not exactly sure which examples you're referring to. We do have a couple of tutorials that are built into Fusion that you can reference. The one that I was referencing, as far as the learning that we're going to hold the office hours for, is under the customersuccess.autodesk.com. I can kind of go to it again here, so you can kind of see when you go into the Learning Hub, under mechanical engineering, as you scroll down, we have a couple of different learning paths, and one is generative design and manufacturing. And so as you come into this and sign in with your Autodesk account, you will be able to download a data set to go through this, and we'll hold that office hours in September.
Somebody asked about the plate steel example. I think that is the
yeah, Claudius Peters.
Claudius Peters, yeah.
One. Let me see if I can grab it real quick.
While you're taking a look for that, I'll go ahead and hit the one underneath that. It says, many of these output examples provided from Generative seem rather complicated manufacturing-wise. Why create a more complicated part when you've already got a design part that is capable of the job? Yeah, Nick, that is it's a good observation, and it's a good question that nobody's put forth before yet. I think a lot of the imagery that is utilized it gets put forth because there's also a bit of it is kind of complicated, but at the same time almost like cool looking, right? So it has that cool factor. Is I haven't seen something like this before, and those outcomes would come from the unrestricted manufacturing method as well as the 3D printed method. But you have a valid point there. So I think for a lot of us who don't live in those worlds, with those manufacturing methods, if you were to focus more on utilizing the milling methods or the 2-axis cutting or excuse me, even the die
Two and a
cast
half axis.
method, like,
Yeah.
yeah, you'd get a lot more outcomes that are maybe a little bit more familiar, right? And probably easier for a wider portion of the community to be able to produce. No.
Yeah, let me add one more thing here. So I'm just sharing. This is from a different slide deck that I have. So this component is one that was human designed, and for a company that we worked with on personal mobility vehicles, and so they wanted to see if they could lighten this any further to ensure that people were able to lift their vehicle and put it into the trunk, right? And so what came of it, I'm just gonna fast forward here. So they got a number of different, maybe I'll go back real quick 1 second. They got a number of different designs out of this. So as you said, right, some are definitely more intricate, more complicated. Some were definitely simpler, right? Looking at a 2-axis cutting one. But ultimately what they kind of looked at was, well, our human design, while it's one in practice, and it's one that we know works, it had a current factor safety of 5. So we could look at redesigning it and a maybe more complicated, 3-axis or 2.5-axis result. We can lighten it and still maintain, what our threshold was of factor safety of 3. And then in their case, taking it a step further, what I really like about this is that while the 3-axis part, to your point, your question, was, over half the weight, realistically, what they then did was took it into our CAM space within Fusion and said, well, let's look at the cycle time. How long will it take, on the machine to compare these, and what's the cost from that perspective. And so their current design that they had was taking about an hour, right? The lightest option out there that they had looked at from a 3-axis perspective was taking about an hour and a half. But that 2.5-axis one that they were able to investigate, that wasn't something they had previously thought of, was only 35 minutes. So there, while they're not getting as much of a weight savings, it's still notably lighter than their current design. And now also machines even faster than their current design. So they're kind of getting a dual win for this specific component. So maybe that kind of helps give a different take on it.
Yeah, good example. Thank you.
Yeah. All right, I'll get out of this. Back to Fusion here. What other questions do we have?
There is, how does one apply constraint regarding torsional bending and direct stress acting simultaneously on a particular part of our model? You have the example up there, right?
Mm-hmm.
We can just show what's available for loads and constraints here.
Yeah. So from a load perspective, I mean, while I may be wanting to see more about the specific model to advise more appropriately, as you get into assigning like maybe a moment or even a remote force, those could be leveraged on the same face. There's no specific requirement that says you can only put for a given load case a single force on a given face or a given edge. So you could, while I have these 2 faces with a given force, I could put another one in there to represent a remote load or some other bending action happening on that same face. I will see, hold on. There was one earlier here.
Okay.
So dealing with CNC programming, is generative design useful in creating surfaces or sheet metal components? I think we talked a little bit about that around the sheet metal side. It kind of depends on what you're getting into and what you want out of the sheet metal part itself. You know, if we had a complicated enclosure, you know, there are times where people have taken given panels and optimized, you know, the layout of where we can minimize material and, you know, and still maintain its strength and its rigidity. But, you know, at this time, what we're not giving you is, you know, where we might need to introduce, you know, stiffening ribs and things of that sort, you know, additional sheet metal features for strength. It is something that our product team is looking into further.
I didn't see that question.
Yeah. And then working with aluminum extrusions, can generative design be applied to extrusion design? That's an interesting question. I can't say I've thought of that one specifically recently.
Yeah.
I,
We're both thinking through that one right now. You know, extrusion is not a manufacturing method input right now. I'm just trying to think out loud, so feel free to jump in, Apollo, if you think of anything.
yeah,
As far as the inputs to the program, you know, it's really going to be more on what that part experiences post-manufacturing, right? Like how is it held? What are the loads on it? Obviously, the material is an input, right? So from that point, generative design will help in terms of, you know, what it might look like. But yeah, you'd have to, then you'd have to certainly evaluate whether it's manufacturable via extrusion, right?
yeah. So my two thoughts, just thinking top of mind. So, you know, if we're talking about the part is extruded itself, so, you know, we'll just pretend that we're talking about extruding like a gutter. You know, if you think about the shape of some of those extruded parts, it is continual, right? And so if the loads are happening, you know, in such a way that if you were to take a slice of that extruded part and constrain it, then, you know, you could look at that from a two-axis cutting perspective, right? So it'd be kind of similar
Mm.
to pretending that we just took a, you know, a 1-inch segment of a, you know, 100-foot long gutter and we're putting loads that may handle in that plane, right? You know, beyond that, like if it was a little bit more complicated geometry, you know, extrusion you could maybe say is similar to die casting if you were to restrict the, you know, the details to simulate, you know, your extrusion. So, you know, it obviously from a given direction, right? So, you know, if we were doing, you know, die casting here, and you can kind of see this, I'll jump to results in a second. You know, for a die cast model, if you look at some of the results when we're, you know, looking at along a given axis, we take into account, you know, the draft angle. And so, you know, perhaps from your end being an extrusion part, you know, that draft angle would be 0 because it's a continual feed of material. And so you might be able to leverage, you know, the die casting results as a method of getting a, you know, say an extrudable part. So if I kind of jump real quick back over here and we'll look at just die casting, you know, you can kind of see that for some of these, you know, maybe ignore the middle section for a second because that's, you know, where the mold might be split. But, you know, along this rear section, you know, this is somewhat like an extruded piece. So you know, in that aspect, you could take that approach. There's another question around, can we design parts where fluid structure interactions is present? So at this stage, we do not have, you know, say a CFD solver in generative design. You know, if you have run, if you're looking at trying to optimize the strength of you know, in that example, you know, the strength of an impeller, and you're trying to maintain the existing surface topology, then, you know, we're kind of optimizing what's going on inside of the impeller itself. And in that case, it'd be a matter of, you know, just assigning appropriate, you know, loads and constraints. And so you could assign, you know, hydrostatic pressures or pressures to represent the different forces acting on those impeller blades and where they are. And then, you know, we would design, or we would, you know, produce those outputs for, you know, what the interior structure of that impeller might need to be to withhold those. Yeah, so we did post a link to everybody for the Claudius Peters one, if you wanted to look at that around some of their sheet steel, you know, items there. And then we will be posting this recording online, you know, shortly after the webinar.
All right. I think that covers all the current questions, right?
Yeah. Yeah, I don't see any other questions at this point. You know, if you do have any other questions, feel free to ask. Otherwise, like we mentioned, you know, if you're looking to get started, you know, using generative design, you know, as you close out of the webinar, you know, feel free to answer yes to the poll that happens at the end. You know, we can reach out and talk more. Otherwise, if you'd like to, you know, step through the generative course that's posted on our Customer Success Hub, feel free to do so. And next month we will take time to go through questions, you know, around that content.
Yeah, great chat today, everybody. Thank you.
All right. Yeah, if there are no other questions, then yeah, appreciate everybody's time, and thanks for attending.
Thank you.